So this is just going to be a little bit of introduction for those of you who weren't in my class this last semester on structural equation modeling, just to get everybody on the same page, give you some background information, just so we don't have to spend a whole lot of time in class not coding, so we can spend more time figuring out how to exactly do this in R when we're all together on Friday. So general definition sort of structural equation modeling is that there is a hypothesized underlying structure that you have sort of created from hypotheses and reading the literature, um, that there is a structure underlying your question or to nature that you can translate into a series of mathematical equations that you can then model against your data to support or refute your proposed structure. So I'm going to start off with two kind of basic points about structural equation modeling. And the first is that structural equation models are directional. They assume that one variable causes another. In this case, that x1 causes y1. And what we mean by causality is that we structure these models assuming that x directly affects y, not the other way around, right? Y doesn't cause x. So x then is a cause of y if we can change y by manipulating x. So it doesn't assume ultimate causation, but it is directional, assuming that x affects y and not the other way around. Okay, so the second key point and cool thing about structural equation modeling is that you can get information about both direct and indirect effects in a system. So if this was your model here, you would be seeing the direct effect of x1 on y3, but you could also see indirect effects of x1 through y2 going to y3, then also through y1, y2 to y3. So not only just the direct effect, also the indirect effects by changing these other variables which have an impact on y3. This is just sort of another example of that, where here you have these sort of direct effect of predator biomass on herbivore and a direct effect of herbivore on kelp. But you also have this indirect effect of otters, right, through the effect of otters on urchins. Another way you could look at this is if you thought diversity was important, maybe you would have that directly impacting your predator and herbivore biomass. And then maybe having predator or otter biomass affecting herbivore diversity and through that way affecting biomass. So there are lots of different ways you can draw these models, so it's important to think pretty carefully about what you really think is happening in your system. So again, our key points, SEM is directional. It assumes that X causes Y, for example, depending on how you draw your arrows in your system. And the second key point is that by combining these inferences across the different equations, SEM addresses both direct effects, but also indirect effects. So you can kind of see the total effect of a variable in your entire system by combining both of those impacts. So that's kind of a cool thing. All right, so here is sort of an example. It's a marine ecology example from a friend of mine, Jarrett Burns, and some of his colleagues, but sort of a fun example. He has a really nice animation, so you'll see that now. Okay, so this is thinking about seagrass and what helps seagrass survive or not survive, as the case may be. And I'm told the existing paradigm for eelgrass beds, at least in temperate systems, is that runoff and other drivers of eutrophication quickly cause eelgrass to become overgrown with fouling micro and macro algae, and then the eelgrass die. However, luckily for the eelgrass, epifauna, little bugs basically, are really good at grazing down algae. So we can see what this looks like. Here's our nutrients coming in, and along with them come these macro and micro algae that result in the eelgrass not looking so good. But then we can have our epiphauna, which is sort of this range of bugs that come in and eat up the algae and allow the eelgrass to get light and nutrients, and the bugs are happy too. They were doing a happy dance there, which I appreciate. Okay, so to test this idea, these researchers wanted to know what are the relative influences of top-down versus bottom-up controls in seagrass ecosystems. So top down, they're thinking about the herbivores. Bottom up, they're thinking about nutrients. So they did this factorial experiment where they had a control, nutrients, or adding nutrients, and then they added a deterrent, basically a pesticide to drive down the epifauna, or deterrents and nutrients. And they did this all in plots in the ocean, which to me seems really remarkable as a terrestrial ecologist that you can do this sort of thing underwater. But look, you can. That's kind of amazing to me somehow. So you can see all of this, all of that fuzz in there is the the microalgae and some macroalgae in there too, and the eelgrass or the seagrass not looking so good in there. Okay, so this is what the researchers initially did before they met my friend and learned how to do SEM. And there's nothing really wrong with doing it this way. It's just that you can probably learn a lot more about what is actually going on in the system by using a structural equation model. And we'll kind of step through that here. Okay, so here is what a really basic ANOVA might look like, right? Where you say that epiphytes, which are also just another word for the microalgae, which is this fuzz in the picture here, are a function of pesticide, right? So here you can see that the pesticides increase microalgae. So maybe you can scratch your head and think that, you know, that doesn't really get at the mechanism driving the success of the microalgae, right? The pesticide doesn't directly promote microalgae. There's something else going on there that we're not capturing in this model. Okay, so an ANCOVA might look like this with the microalgae, again, that's the epiphytes here, being impacted positively by the pesticides, and the pesticides are increasing the microalgae more than their habitat, which is the seagrass, or their substrate increases them. Or the habitat is their substrate. And then this is the macroalgae that we added in here, which seem to have a slight negative impact on the microalgae. So it's just the bigger algae that's living in the seagrass. Okay, so here we have our first SEM. This is a relatively simple one. We have our pesticide. We're saying that now we think our pesticide is having a negative impact on our epifauna, right? The bugs basically that eat down the microalgae. So they should also have a negative impact on the microalgae. Microalgae still, this is their habitat, that should make them happy. And we don't really know that much about the relationship between the macroalgae and the microalgae, but in this case it's saying it's a positive effect. So here we've seen pesticide reduces the epifauna, which releases the microalgae from grazing. Macroalgae and seagrass provide habitat for epifauna, or the microalgae in this case. Or no, sorry, for the epifauna. They provide a habitat for epifauna. This is the seagrass and the macroalgae. And substrate for the microalgae, so promoting grazing. So we've learned quite a bit more about why pesticides might help out the microalgae. And then we have this full SEM where they've put in two different kinds of epifauna. This is caprolid, this crazy looking thing over here. These are gammarids, these guys over here. And I'm not going to walk through every arrow here, but the upshot is that the pesticides reduce the epifauna, both kinds, which in turn release the microalgae from grazing. The gammarids over here appear to really control the epiphytes more strongly in the system. And the macroalgae provides a habitat for the epifauna, promoting grazing, while the eelgrass provides substrate for the microalgae, food and shelter, basically. All right. So really the key here is that you just gain substantially more information about this system when you move into an SEM framework, and particularly with this full SEM than you would with a bunch of ANOVA and ANCOVA tables. You learn much more about the mechanisms driving what's actually going on. So you're getting this increasing inference. You can tease out complex relationships, identify and compare direct versus indirect effects. What are the potential mediators of certain impacts? And get more precise mechanistic explanations. So Here, now you go walk around and then you can come back and watch a video about definitions because that's super exciting. All right, thanks. And I'll see you guys Friday.